Alright guys, round 2 on predicting products, a single replacement and double replacement. And like I said in class, we'll worry about net ionics together in class tomorrow just to make sure we're all on the same page. So right now it's just kind of getting the basic gist of them. Single replacement and double replacement will differ from synthesis and decomposition that we looked at today due to the fact that if you look at the reaction, there's two substances on both sides of the arrow, at least two substances on both sides of the arrow. Remember with synthesis, there would have only been one thing on the product. Instead of this plus sign, it would have just been like AC or just the B. Versus decomposition, there was only one thing on the reactant side. Here, there's both things on both sides of the arrow. There's at least two things on both sides of the arrow. Single replacement will differ than double replacement in the fact that it's an element replacing an element in a compound. So you have an individual element like C kicking out B, forming AC, a new compound, and then B is left by itself. I always remember it where there's somebody by themselves or single on both sides of the arrow. Okay, so whether the reaction will occur though is all dependent on the activation series, which I'll show you in just a minute. Now again, just like with synthesis and decomposition, we have several types, but let's just kind of look at some of the models and not worry about the types so much right now. Okay, here's our activation series. The activation series is our reactivation series. It can be called either one, is dealing with how reactive the metal is. You'll look at something a little bit later this week which is called reduction potentials, which is really the same series, and that will be given to you on the AP test, so that makes your life a little bit easier. You don't have to have this memorized. There's something to kind of keep in mind. The further up it is on the periodic table, like lithium and fluorine, the more reactive it is. The farther down it is, for example, gold and silver and platinum are down here, the less reactive it is. Okay? And again, this isn't something to memorize, but notice this, that here are our metals, and here are our non-metals, and these will react in different reactions. A metal will only replace a metal, a non-metal will only replace a non-metal, and these are the basics. There are other ones, but these are the primary ones that we're used to seeing. Okay, so again, just kind of looking at the types, but again, let's not worry about the types. Let's just kind of look at some of the models. We have calcium chloride, which in this case is going to be CaCl2. We'll worry about states of matter tomorrow in class when we talk about our net ionic. But we have calcium chloride reacting with copper, and it does say in water. So calcium chloride would be aqueous, and then of course copper is going to be solid because it is elemental copper. Again, we'll worry about states of matter in class. Now, what we need to do with our activation series is determine if copper is more reactive than calcium. Again, remember the metal will always replace the metal. Copper is not going to touch chlorine at all because chlorine's a non-metal. So we jump back here to our activation series, and we find calcium, which is up here at the top, and we find copper, which is down here at the bottom. Now, because copper is less reactive than calcium, it's not going to produce a reaction here. Copper will not replace the calcium. Alright, so due to that, what we're going to do here is say that this will produce no reaction. There's no reaction between calcium chloride and copper because copper cannot replace calcium. The idea here is our individual element has to be more reactive than the one it's replacing in the compound. So let's look at the next one, silver nitrate plus copper. So again, if I go back, and again, notice this is in water, so this would be aqueous, and copper would still be its metal. Let's go back and look at our activation series. We have copper, which is still down here, and we have silver below it. Copper is more reactive than silver, which means this will react. Copper will kick silver out and will form with nitrate. And again, we have to assume the most common charge of copper, which is going to be +2 unless we're told otherwise. So this is going to form copper 2 nitrate, so CuNO3 2, and silver metal. And again, the compound would still be aqueous, but we'll deal with states of matter tomorrow. Okay, let's jump down here and say we're looking at our nonmetals. Okay, lithium chloride is LiCl, and again in water, so this would be aqueous, plus fluorine, which is F2. Jump back here. Fluorine is more reactive than chlorine. which means the reaction will occur. So fluorine's going to come in, kick chlorine out, and what we're going to end up with is LiF and Cl2. Okay, same thing down here, bromine and iodine. Due to the fact that iodine is less reactive than bromine, this is going to produce no reaction. And just so you can see that, bromine's up here, it's the one in the compound. It is more reactive than iodine, which is our individual element. Okay. So let's keep looking at these. These are looking at hydrogen. So we have nitric acid, which is HNO3, reacting with sodium. Again, let's just go back and quickly look at our activation series. These are metals. Hydrogen is considered a metal. So we see hydrogen here, and all these metals are more reactive than hydrogen. So notice sodium is definitely more reactive. So we go back here, sodium's going to kick out hydrogen. We're going to end up with sodium nitrate and hydrogen gas. Okay, same thing down here, carbonic acid, H2CO3, reacting with gold. Gold's one of our least reactive. It is not more reactive than hydrogen. Again, just so you see, hydrogen's in the middle, gold's all the way down at the bottom. Okay, no reaction is going to occur. Sodium reacting with water, we just saw sodium is more reactive than hydrogen up in the above one, so we can see that again. This is why our reactions with our alkali metals are very, very nasty, very violent. Sodium's going to come in and kick out the hydrogen, and what we're going to end up with is NaOH, because remember we can think of water as HOH. It's just removing one of the hydrogens, leaving the hydroxide, and then we're left with hydrogen gas. This buildup of gas is what can be very, very violent. Same reaction will occur with magnesium in water, Mg plus H2O. Magnesium is higher than hydrogen. And you can go back and look at the activation series if you want to see that. So we end up with Mg, OH2, and H2O. And of course you'd have to go back and balance these. Okay, so that's really it for single replacement reactions. You're just using your activation series to determine if it's going to react or not. Double replacements, again, we're looking at two things on both sides of the arrow, but notice here, both things are compounds. We don't have anybody single or by themselves. There are, again, different types of double replacements. What's important here is our states of matter, and we'll look at net ionic equations, but what we're looking for is anything that's not aqueous, are soluble in water. Remember, our precipitants are solid compounds, or compounds that form in an aqueous solution, or solid compounds that form in an aqueous solution. Water, of course, will be a liquid, not aqueous. Water cannot be dissolved in water. And then gas, of course, is also not aqueous in that term. So these are kind of our states of matter we're looking for. So let's just kind of go through, look at our solubility rules. You're not going to have to memorize these. It doesn't hurt to know them. Again, knowing that your group 1 elements, your alkali metals are always soluble, etc. But I would probably try to find yours from last year or the year before, depending on when you took regular chemistry, or find a good one offline. I don't know if I would suggest this one. It looks like with the halogens, it's not including bromine, which I would include the bromine in there because it follows the same rule as chlorine and iodine. It's not including fluorine, which is not following the same rule as chlorine and iodine. It is not soluble with a lot of different things. So I would grab a different solubility rule chart offline, but I would definitely have one. So let's just kind of go through and look at these. We have sodium chloride, which is NaCl, plus silver nitrate, Ag, NO3. So again, notice they're both compounds. These reactions will always occur. So we're going to end up with sodium nitrate, and we're just following our charges as we're doing these. Everything in here is a 1. And then silver chloride. Now, silver chloride, if we go back and look at our solubility rules, chlorine is soluble except with silver, mercury, and lead. So this is forming a precipitant, or a solid. And again, that's going to be important when we look at net ionic equations. Something important with double replacement reactions is they're always occurring in water, which means we will always have aqueous substances. Okay, sodium carbonate, Na2, CO3 plus copper 2 chloride, CuCl2. Again, the question is not whether the reaction will occur or not, it's what's formed. So sodium will form with chlorine, both are 1, so NaCl, and copper will form with carbonate. Both are 2, and we are given the charge of copper here, so that helps us out. So CuCO3. And again, if we go back and look at our carbonates, most carbonates are insoluble, so this would be our precipitant. Okay. Forming of water. These are typically called acid-base reactions as well. HCl plus sodium hydroxide is going to form sodium chloride. Okay, so the sodium and chlorine will hook up, and then the HOA will hook up, which is water. Again, these are occurring in water, and knowing that water is a liquid is important. Carbonic acid, H2CO3, plus barium hydroxide, BaOH2. We're going to end up with barium carbonate, okay, and H2O. And last but not least, the formation of the gases. Again, I wouldn't bother necessarily memorizing these, but I would definitely be able to recognize them when they occur. And we have, of course, our carbonate, our carbonic acid when it forms, and these are when they form as products. Specifically, if carbonic acid forms, it breaks into carbon dioxide and water. This is what we see when we mix baking soda and vinegar. Baking soda is sodium bicarbonate, and vinegar is acetic acid, HC2H3O2. Okay, what this forms is sodium acetate and carbonic acid. So it ends up breaking down to carbon dioxide and water, which is why we see the gas forming, or the bubble. Ammonium hydroxide, when it forms, breaks down into ammonia gas and water, and then sulfuric acid, if it forms, will break into sulfur dioxide and water. And then, of course, we do have 2 other gas products. Again, this is just a recognizing. It's not a memorization. Just recognize that these can occur. Okay, so looking at these, sodium bicarbonate as acetic acid is what we just saw. So just to see it again, sodium bicarbonate is baking soda plus acetic acid. Okay, is going to form sodium acetate and water and carbon dioxide, because these 2 are technically H2CO3, but it breaks down instantaneously. So seeing these 3 products can be a little bit confusing, or a little bit weird. Same thing here with ammonium chloride and sodium hydroxide, NH4Cl plus NaOH is going to form sodium chloride, and then ammonium hydroxide, which is going to break down into NH3 and H2O. Okay, this is what formed, but it doesn't actually form because it instantaneously breaks down into these. Okay, and our last one, iron 2 sulfide plus HCl. When this reaction occurs, it's going to form iron chloride and hydrosulfuric acid, which is our gas. Okay, that's it for double and single replacement reactions. We're going to focus quite a bit on writing these into net ionic equations tomorrow. Just make sure you come in with any questions that you have. Thanks, guys.